Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is the fifth in a playlist on regression. The video covers some basics in regression analysis that apply to the three types of regression analysis covered in these videos: simple linear, multiple linear, and simple nonlinear. See statisticsfromatoz.com/videos for the latest status of my videos. As usual in the book and in these videos, we'll go quickly through a list of keys to understanding, or KTUs, to give you the overall picture on one page. And then we'll go into detailed explanations of each of the keys. For this video, there are three KTUs. The first key tells us that different disciplines have different standards for what is good enough, a good enough goodness of fit, as measured by R squared. And it goes on to say, an R squared which meets the desired clip level is necessary, but not sufficient. The second key states the residual for each xy data point is the difference between y hat, which is the value predicted by the model, and the actual value of y. And analysis of residuals is essential in assessing the validity of the model. The third and final KTU provides three cautions. First, cause and effect cannot be determined by statistics alone. Next, regression predictions must be tested with experiments on new data. And third, never attempt to predict, that is to extrapolate, beyond the range of the x variable in the data. And here on one page are the three keys to understanding the analysis basics of regression. You may wish to pause the video at this point and read them all together. Now let's go into detail on each of the three keys. How large a value of R squared would we need in order to conclude that our regression line or curve is a good fit for the data? Well, that depends on the type of analysis that we are doing. The first key starts out by saying different disciplines have different standards for what is a good enough goodness of fit as measured by R squared. In the physical sciences and in engineering, there are laws of science that determine the behavior which we are measuring. So we should expect a higher degree of accuracy than in social sciences, where human behavior cannot be precisely predicted. As the table shows, we might require that the R squared be 0.9 or better in order for us to conclude that our regression model is a good fit. In the social sciences, on the other hand, we may have to settle for 0.3 being as good a fit as we're going to get. And in process improvement disciplines like Six Sigma, they might require 0.7. If the model does not meet the desired clip level for R squared, then a different x variable or additional x variables can be tried. However, even if we have an R squared which meets the desired clip level, there are still a couple more hurdles to clear before we can say we have a good fit. KTU number 2 tells us of the first hurdle, residuals. The residual for each xy data point is the difference between y hat, which is the value predicted by the model, and the actual value of y in the data. Here you can see a number of xy data points and the simple linear regression line that has the best fit for this data. For each x in an xy point, y hat is the y value on the regression line associated with that value of x. In this example, none of the points is on the line. For each value of x, the corresponding y value on the regression line is different from the y value in the data point. For each data point, the residual is the difference between the value of y in the data point and its corresponding value of y hat on the line. The value of each residual is depicted here as the length of the dotted vertical line from the data point to the regression line. KTU number 2 goes on to say, analysis of residuals is essential in assessing the validity of the model. This is covered in detail in a separate video titled Residuals, which is part of this playlist, but here are some requirements that are part of that residual analysis. Residuals must be random, and they must be normally distributed. They must not be correlated with any x variable. They must not be autocorrelated relative to a time sequence. They must have constant variance, and they must have no unexplained outliers. Again, these will be covered in detail in a separate video. Most of these requirements are just different ways for specifying randomness. If residuals are not random, then there may be one or more additional X factors which are causing the non-random behavior, and so our regression model would not be complete. A purpose of regression is to identify and quantify cause and effect relationships. Key to understanding number 3 starts out by saying that cause and effect cannot be determined by statistics alone. It is important to engage human subject matter experts to describe credible real-life mechanisms or scenarios by which the correlation we observe can be explained by X causing Y. If it's a mystery why there is a correlation, then there could be other explanations. For example, an unknown lurking variable could be causing the variation in both X and Y. In regression, we strive to develop a cause and effect model in the form of an equation. The model predicts what future, that is, yet to be collected, data will be like. For simple linear regression, the model is the equation y equals bx plus a, which describes a best fit straight line in 2 dimensions. The second caution in key number 3 is that regression predictions must be tested with experiments on new data. If we have a value for r squared above our clip level, and if we have compliant residuals, then we can proceed to the next stage of analysis, a controlled or designed experiment. We cannot use the original data as proof of cause and effect. If we want to use the model to predict values for y, then we must actually collect some new data, use the model to predict some new values, and then test the model's predictions with designed experiments. Design of experiments, or DOE, is a fairly complicated discipline in its own right. There is a 3-part series of articles in the book on this subject, and I plan to produce 3 videos about it. As the diagram shows, first we must have linear correlation if we want to attempt linear regression. Then we consult with subject matter experts to come up with likely causes. Then we collect some data and identify a best fit regression line or curve, which is called our model. And if designed experiments using new data demonstrate that the regression model is valid, then and only then can we claim that we have demonstrated that our x's do indeed cause the y. Probably the biggest no-no is extrapolation. Never predict beyond the range of the x variable in the data. Let's say that there is a clinical trial of a new drug which tested dosages ranging from 0, which would be a placebo, to 30 milligrams. To keep things simple for this illustration, let's just show the results from 2 subjects tested at each dosage. The resulting XY data, which is shown in this left diagram, indicates a close fit to a regression line which show that increasing the x dosage, increasing the dosage, which is the x variable, increases the subject's health outcome, which is the y variable, proportionally. Now, if the experimenters knew little about statistics and had little common sense, they might be tempted to call a press conference announcing that they had proved that larger and larger doses of the drug produce better and better results, as shown in the second graph. They would then be extrapolating their findings beyond the range of the dosage, which is the x variable values, which they tested. Fortunately, wiser heads prevailed, and they announced that their test results were only valid for 0 to 30 milligrams. Later, additional research tested doses from 40 to 50 milligrams, as shown in the third diagram. Those actually resulted in poorer health outcomes than those for 30 milligrams. This little cartoon may help you remember the point. If 3 pills are 3 times as good as 1 pill, that does not mean that 10 pills will be 10 times as good. In fact, 10 pills would probably land you in the emergency room of a hospital. In this video, we have referred to 3 previous videos in the playlist, and on this slide you can also see the next videos which are planned at this point. The one listed last, ANOVA versus regression, was completed a while ago as part of the playlist on ANOVA. For the latest status of my videos, please see the videos page of the book's website. Okay, that concludes our clarification of the concept of analysis basics for regression. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60 plus concepts in the book if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job, while studying, or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page Statistics from A to Z and on Twitter as @StatsA to Z.